Okay, let's talk about the fundamental theorem of algebra. As you can imagine, this is pretty important. It's fundamental to the study of algebra. And what it actually says is that every polynomial with real coefficients, that's not written in here, but it should be, every polynomial you can imagine with real coefficients has at least one complex zero. One complex number you can plug in that makes the whole function equal to zero. And an easy to prove corollary of that says, okay, you got a polynomial of degree n, then not only do you have one complex zero, you must have n of them. So the degree of the polynomial tells you exactly how many zeros you will have, how many different complex numbers will make that function equal to zero. And the factor theorem says that if you know a root or a zero, you also know a factor. So if the degree is n, your polynomial can be factored into n linear factors, x minus c1, c2, and so forth, where these are the zeros, also known as the roots. And these may be complex numbers. Now, there's nothing that says these have to be distinct. You can have repeats in this list. So does this mean that every polynomial has imaginary zeros? No. Remember, real numbers are complex numbers. The number 3 is 3 plus 0i. It is a complex number. The set of all real numbers is a subset of all the complex numbers. Okay, so if we put this all together, the factor theorem, the remainder theorem, the fundamental theorem of algebra, we get this. So you've got yourself a polynomial with real coefficients. Then for some number c, a complex number, these 7 things all say exactly the same thing. These are equivalent. F of c is 0. C makes the function 0. That means the same thing as calling c a root or a 0. Those two words are synonyms in the case of polynomials. We'll use them interchangeably. Sometimes we'll say roots, sometimes we'll say zeros. So another way of saying that is C is a solution to the equation f of x equals 0. Now, if C happened to be a real number, remember all of this is true for any complex number. If C happens to be a real number, then not only do you know yourself a root, you also know an x-intercept. You also know a factor. This is true no matter what, even if C is complex. Roots correspond with factors. The remainder theorem says if you know yourself a root, you know that if you divide the polynomial by x minus that root, your remainder is going to be 0. So all of these say the same thing. Now keep in mind, not all roots are real numbers. We can have complex roots, but complex roots don't give us x-intercepts. And we'll see in another video that complex roots always come as pairs. You'll never have 2 plus 3i as a root unless you also have 2 minus 3i. Okay, so you got yourself a polynomial with degree n, then you know you're guaranteed you're going to have n roots. If the degree is 7, you're going to have 7 roots. Not necessarily distinct. You might have repeats in that list. You're going to have 7 factors. Again, not necessarily distinct. You would have at most 7 x-intercepts. Remember, if you have repeats in this list, then if 2 is a root and that appears 3 times in your list, you can't hit the x-intercept 3 different times at the same spot. So if we have a multiplicity of a root that's not 1, then our number of x-intercepts will be less than n. So the degree is n, we're going to have at most n x-intercepts. If we have complex roots, they don't give us x-intercepts. And then polynomials, they curve, right? They have those turning points, those local highs and lows. A polynomial of degree n will have at most n minus 1 turning points. So a third degree polynomial could have at most 2 turning points. That's a good place to stop.